Okay, with light energy, the bromine will rupture. The bromine bond will rupture or cleave. Single hook, fish hook arrow, one electron moving this way, one electron moving that way. When one electron moves this way, we just have one electron. Now when that goes that way, you get the same exact thing on the other side, right? So we can just say this, two of those. Now that's different from like maybe taking HBr and both electrons going this way. This would give H plus because of no electrons, and we would get, what's the fourth thing here with this? Lone pair, both electrons. Well, this is ions. It's called ionization. Okay. This is called also called heterolytic bond cleavage. More simply known as ionization. Hetero meaning
two different atoms. Explain.
it's not two different atoms. It's the outcome is different. Here you got a minus, here you got a plus. Compared to over here, this is called homolytic. Bond cleavage. It sort of cleaves the same way. One electron, you got the same outcome. Where over here, both electrons went one way and left the other guy with none. Homolytic bond cleavage promoted by the light energy, and we can get bromine radicals. This is pretty easy to do. Again, in this reaction, we didn't make any radicals, did we? The alkene attacked the bromine and kicked it off. It was okay. It was not a radical reaction. It was an ionic, all ions. Okay, from there, this bromine radical will strip an H out of an alkane. We draw our compound here. There's an H here. It'll abstract the H, or we can show mechanism. One electron here, two electrons in this bond. One electron comes here and teams up. One electron teams up with this electron. The other electron we're going to leave behind. What does this arrow movement give? Well, the Br electron is teaming up with an H electron. So what does that give? Making a bond when they team up. Two electrons teamed up. You see it?
Yeah, starting to get it.
See it? A bromine electron teams up with an H electron. Okay? But the other electron here in this bond stayed on the carbon. So what do we get over there? Boom, boom, boom. The other electron stayed here. Okay? There used to be two electrons in this bond, but one went teamed up with that, and the nucleus went with it. The other electron stayed here. And we can say that the bromine stripped an H out, but we're going to form HBr. There's your HBr right there. Okay? What do we form here? Well, what do you call something with a single electron? Radical. That's a bromine radical. What do we have here? Carbon radicals. Okay? And what's the charge of the carbon radical?
Neutral.
It's neutral, because that carbon owns one electron of each bond, and then it owns the single electron for a total of 4. It's supposed to own 4. It's neutral. And when we make radicals in mass spec, they're neutral too. Now the question is, why do we make radical there? Why didn't the bromine strip an H from some other carbon?
Tertiary.
Because it's tertiary. Tertiary radicals. A radical is electron poor. Does everybody agree? Does this carbon have an octet? No. 2, 4, 6, 7. It's missing an electron. It does not have an octet. So it's electron poor. Just like a carbocation. Carbocation would be even more electron poor. But a radical is electron poor. Thus, you stabilize radicals the same way you stabilize cations. Okay? And thus, a radical on a tertiary site would be more stable. Why? Because of the induction, right? Just like if it was a cation, we'd say more induction, tertiary better. So that's where you're going to form the radical. Okay, how do we get our final organic product?
Another radical.
We got another bromine radical. We formed two over here. We could say that the bromine electron teams up with the carbon electron to make the CBr bond. Okay? That is, this electron and this electron team up and make a bond. And that would give boop, 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 boop. And now they've teamed up. Now they're bonding together, holding those nuclei together. There's your end product. And we use 2 Br radicals that we form. The only problem is that's not the mechanism. The reason that's not the mechanism is because this doesn't jive with all the knowledge that we know about this reaction. The light or the heat is only needed at the beginning. Once the reaction gets going, you can turn the light off and it will keep going. Now, if this is the mechanism, and we did one reaction, now if you do a gram of starting material, or half a gram, you've got to do how many reactions? Well, a gram of that starting material has got, you can do the calculation, it's got like 100 gazillion molecules. That means you've got to do this 100 gazillion times. Well, that means you've got to rupture this 100 gazillion of these. And maybe it takes 2 or 3 hours to do the reaction. I mean, it all just doesn't happen like that. Well, if you've got to cleave 100 gazillion of these and the light is cleaving it, you should have to keep the light on, right? But we know that you can turn the light off and the reaction will keep going. So how does it keep going with the light off if you've got to cleave 100 gazillion of these?
Does the carbon radical cleave because it wants to be happy more than the bromines?
I thought you were on to something. Here's how, from here, here's how we get there. Instead of this reacting with bromine radical, we can say it reacts with bromine.
Yeah, that's what I'm saying. It cleaves the bromines.
Okay, and what happens is, this electron will team up with one of these, and it will help cleave this. And one of these electrons will come team up, and the other electron goes here. And what does this do? Well, this also gives product, because this electron is teaming up with a bromine electron to make the big old CBr bond. I'll redraw it.
I guess it should have H plus I.
But importantly, what else does this form?
Another bromine radical.
This mechanistic proposition reforms another bromine radical, where that one sort of just quenches them all and consumes them all. Now, since we reformed a bromine radical, what can it now do? It can come over here and strip an H out of the next molecule here, form there, and this can react with the more. At this point, you just can build a cycle, because every time you produce product, you produce bromine radicals. At this point, you can turn the light off, and the reaction will produce its own bromine radicals. So that's an important point in the mechanism. Your mechanism has to support all of the known information. It has to support stereochemistry outcomes. It has to obviously support the formation of products. It also has to support some type of practical knowledge.
So, if you have bromine in that alkane, eventually, I imagine, just through chance, you're going to get, if you have so many of them, bromine that radicalizes on its own. So will that eventually just like look fine forever and spontaneously at some point change over
Change over to what?
to the product? Just because it only takes one to start the chain reaction? In other words, would this eventually happen without light because one of them just incidentally became a radical just because it had a lot of energy or just felt like it one day?
Oh, you might, yeah. But just the light from this room may be enough to get it going. Yeah, you don't want to start combining alkanes with bromines. It's probably going to react with bromine.
The termination of the reaction is where the radical actually,
The regiochemistry. Why do we get the bromine bonded to this here? Yes, that's the reason for the regioselectivity, because you're going to make tertiary radicals, and thus it's going to capture the bromine and you're going to get there. You would not predict we're going to make radical here because that would be a primary radical. Okay, so this is a fairly selective reaction. Okay, you're going to get the best radical, just like you get the best cation. But this is called propagation. Propagation is where you set up the cycle and you can just cycle through. Okay? That's important. Now, this here would be called initiation. You know, shining a light, the initiation. But then it can propagate on itself and you can turn the light off. This final step can be called termination. No, I don't think that's part of propagation. There could be some termination steps here. For example, this would be called termination. I mean, this could capture a bromine radical. Why not? But if it did, you would call that a termination. Termination step. I mean, you could. Okay. What could be other possible termination steps?
bromine recombining with itself.
Bromine could recombine, yeah. Because if it did, then you would have to come back and say you need more light to rupture it back again. Or side products. Let me ask you this. Is it possible to maybe form possible to get that product there, which looks like a dimer? How would you get that?
Two radicals hit each other.
Two carbon radicals coming together and making a bond? Yeah, that's possible.
So that would that imply that the carbon radical wasn't the sp3 one? I mean, wasn't the tertiary one?
No, this is where we made this bond here. A tertiary radical bonded, teamed up with a tertiary radical.
I got you.
Very often radical reactions can be a little messy and have side products because these radicals can start combining. Okay. Very often it's driven by your thermodynamics. And if you do some calculations, you'll see that a CBr bond is pretty strong. And here's sort of a important thing. Why are we just doing bromination? That's because it turns out that bromination using bromine has just good thermodynamics, and you can get this product in reasonable yield. If you try to do like chlorine here, it doesn't work as well. Because the chlorine radical is so much more reactive, it's not as selective. And it'll strip H's from all over. Where the bromine radical is not so reactive, it'll be more selective for the tertiary radical. Of course, fluorine, you better stand back. It's just going to go haywire and just strip any H's and just get boom. It's going to be so fast. Typically, reactions are fast. Well, it's maybe overgeneralizing, but they may not be that selective. Iodine, on the other hand, iodine radical is so lazy, it just won't react. And actually, if this was iodine, that would be an endothermic reaction if you do calculations. Okay? And actually, a lot of your alkyl iodide compounds will actually go backwards and form alkane and release iodine. That's why maybe this compound, maybe when you initially distill it, it may be colorless, but a year later it may be kind of light brown. That's because with time it converted to this plus iodine. We'd have to balance that somewhere. We need another H. It could maybe come from water or somewhere, but it's the opposite of this. If you do this, this is actually favored thermodynamically. How can we do opposite? Well, we could rupture this carbon-halogen bond just like we ruptured the bromine bond. There would need to be an H source, but in the end, iodine tends to not want to go this way because it's just it's the opposite of fluorine. Fluorine will go that way very energetically. Iodine doesn't go that way that much. Turns out Mother Nature just gave us bromine to be a good reagent for radical halogenation. We can do this mechanism. It's very important for alkanes because, you know, most alkanes come from natural products, natural gas, and they don't have much reactivity otherwise. You can burn them with oxygen. We can also do a radical halogenation. Importantly, once we get the halogen on there, as I say below, we'll do some examples, but once we get the halogen on there, now we can do all types of chemistry. Because now we can start doing substitution chemistry or elimination, and now you can start making all types of things. Well, back over here, it just doesn't have much reactivity. So being able to put the bromine on is very important. Questions about the mechanism, then we'll look at some other examples for different products. Again, don't confuse this with your alkene reaction. Okay, can you show a product here? Like tertiary radical, right? Tertiary radical will capture a bromine radical, or it'll react with bromine to form other bromine radicals. Ultimately, that's you're going to brominate the tertiary radical. Yep. final exam's coming up. First off, what's the stereochemistry of the product?
Should be racemic, right?
Racemic?
These are.
Anybody have another?
Well, it's not even, it's not chiral, so it's
Not chiral.
Oh, yeah.
There's no chirocarbon. It's not going to be racemic. It's going to be just that. Yes, that carbon is tetrahedral, but you can draw it however you want. Okay. What if we treat this with some KOH and heat it up? What would we get? I think this was like number 4 on the test.
replace the bromine.
No, it was one at the bottom. What are we going to get? If we,
You get the double bond.
Elimination reaction.
Brian,
Elimination.
what kind of chemistry could we do now if we treat this with KOH?
Reaction lead for elimination.
You reckon leave in what?
For elimination reactions.
Elimination? And give what product?
A double bond.
Double bond where?
On the Higgs side.
In the ring.
On the right side.
Yes. That'd be E2.
Yeah.
And we're showing the safe product.
Uh-huh.
Then we could react this with maybe, if we reacted this with BH3 followed by sodium hydroxide and H2O2.
OH on the tertiary.
Actually going to have OH here. And we're also going to have stereochemistry because the OH and the methyl are going to be what? OH and methyl are going to be yes. Plus what? Plus an enantiomer because that product is chiral. It's going to be in okay.
So it's the second or final?
What if you then treated this with sodium and then ethyl iodide?
It's going to be substitution.
Alkylation of
alcohol.
You get ether.
No reaction?
You just said the iodine.
Do it?
I said you just said the iodine was like made this.
That's why it's so.
No,
That's
it's not a
for
radical
radical.
reaction, isn't it?
Alright.
Yeah, but it's still
It's a regular reaction now.
Sodium is going to make the alkoxide, right?
Yep.
And then this will do that, and we can get this ether. Now, if you got a mixture of enantiomers there, you're going to alkylate each one. Make this ether. Ethers tend to be end products. I mean, you can cleave the ether, you can react with HBr, and you can maybe get back that. Ethers tend to be end products. But, okay, in the end, you can start with an alkane, get that bromine on there, then you can do lots of things. Okay, instead of H nu or heat, you can also use peroxides. The simplest peroxide is hydrogen peroxide in your medicine cabinet. That can be used sometimes. More commonly, it's this guy, which is condensed. This is your two O's. On each O, you have a CO phenyl. CO phenyl. Anybody know the name of this one, which also may be in your medicine cabinet? That's a benzene, that's called a benzoyl group. What's this? Benzoyl peroxide, yes. Okay. You can use it to treat acne. You can also use it to promote radical. Yeah. Okay, peroxides, I'm not going to show you mechanisms. I can tell you briefly. Basically, the peroxide, like the bromine, will also cleave. But it'll cleave easier. Or maybe just as easy. But when it cleaves and you get peroxide, O radicals, the O radical will help make Br radical. Okay, so we're not really going to look at the mechanism, just know it's very common. Is one way is to include a OO, a peroxide.
Is that why they're always opaque containers?
They are light sensitive, yeah. Because you put a little light on here and the OO will rupture like the bromine will rupture. So it's often included as a way to get the radicals going. So you see this basically doing a radical bromination. Okay, you gotta recognize that. So where are we going to make radical at? Same as cation. Where would you make cation?
Secondary carbon next to the benzyl ring.
Benzylic cation. Benzylic radicals are also very, very stable. Okay? That's going to be your shown product. Benzylic bromination.
That will be racemic.
Yeah, it would be racemic because that is chiral. Basically, when you get that carbon radical, the bromine can approach it from either side to make the carbon-bromine bond. It doesn't have to attack the backside. Okay, NBS. This is NBS. Instead of bromine, it's bromine nitrogen, and the nitrogen is bonded to two carbonyls. Okay, but this will also rupture, and it can supply bromine radicals. What's the difference? Br2 is a very volatile liquid. You open it up, you're going to get vapors all over the place, and it is very hazardous, very reactive. Okay? Radicals, it'll make HBr in the body, you got stuff going on. NBS is a nice white solid. You can weigh it out, let it sit there, it won't chase you around the room. So it's a nice, safer alternative. But it will supply bromine radicals. Anytime you see NBS in bromosuccinimide, it's just bromine radicals. So, where we're going to put a bromine radical, here, what's product? Where would you like to make cation?
Secondary.
Right here.
Yep.
It would be resonance stabilized, okay? Make radical here. I'll go ahead and show the product, then let's look at resonance of that. Here's a radical that we're going to say reform.
Okay.
First off, what's that position called? I don't think we've named it. That's called benzylic, next to the benzene ring. This is called,
Allylic.
how do you know that?
It's the carbon attached to the carbon that's in the double bond.
Okay, somebody else said it too. I thought two people said it. That's called allylic. Next to the alkene, you might think it may be called alkenic or something. It's called allylic. That's benzylic. It's resonance stabilized. How do you do resonance of radicals? Okay? We'll do resonance. One electron, this electron can come here. One of these can come here. The other one can come here. What does that arrow movement give?
Single electron.
One here and one here. What are we making here?
Pi bond.
Pi bond. This electron is moving on to the carbon as a radical. And we get this structure. These are resonance structures. So all I did was move pi electrons. Okay, so the allylic radical is resonance delocalized. Just like the benzylic radical is. We could do resonance with the benzene ring, just like this. Now if we look at structure, boom, 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 we know we got pi bond, one electron overlapping. Then over here we have radical. What's a hybridization of the radical? How many electron regions around that carbon?
4.
4. There's an undrawn H there. It's 4. sp2 or sp3? You can have that. In graduate school, you'll do half.
Oh.
Because really, sp3 is meaningless. It's really bonding. That's why sp3 is 109.5. If it ain't 109.5, it ain't sp3. If it's 107, then it's something else. It's okay. Well, if we're doing resonance, this electron must be in a p orbital. Resonance is a p orbital thing. Yes, it's sp2. What we're saying is that one electron's in a p orbital. Let's see, you've got all this here. What you have is 3 electrons and 3 p orbitals, but you can show this 2 different ways. I mean, if this was a lone pair, what would we say the hybridization was? Anytime a lone pair is next to a p orbital, a lone pair is going to want to be in the p orbital. Well, it's the same thing for a single electron also. Usually, although it doesn't have to always be. So you can do resonance of radicals. Everything we did with carbocations you can do with radicals. So that's where you want to form it. And so this is where then it forms and you get the. That's actually. Ooh, this is actually.
Isn't that double bond more stable since it's more highly substituted?
Yeah, I just realized it. How might you get this product here?
Bulky base.
Could you get this product? This is where you just react the other resonance structure. That would give that. And if these are 2 possible products, how would you say which one's going to be favored?
Remember that?
Yeah, that'd be your major product. Because it's more substituted. That's a disubstituted alkene. This is only a monosubstituted alkene. Now up here, you can do resonance structures and put radical over here, 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 here. But you never brominate over here because that would destroy the aromaticity. So you're not going to. But here, we're not destroying the aromatic ring. Okay, why can't you use bromine in this last example?
Just react with the alkene.
Yeah.
Right, we got the alkene. Okay, and thus we can say something. See here, if you tried to do radical bromination with bromine, it's going to react with the alkene. And actually, it would react there faster because bromine reacts with alkenes like instantaneous. You did it, drop it in, boom. Okay. It turns out that NBS will not react with alkenes. Thus, use of NBS will be selected for just the radical bromination. Thus, if I showed a reaction like this, like we may have showed 3 weeks ago, what's the product of that reaction?
This one is. Molecule dibromine.
Just this, it'd be racemic. Bromine's going to react with the pi bond fastest. Also, usually in a testing situation, although not always, if they want you to do radical, they would have said like H nu. Or peroxide or something. But even still, you got to be careful because in the end, just know that bromine is going to react with an alkene first and fastest. It will not react with the pi Ds, not in this class. To react here, you're going to have to use bromine and like iron or something. Then we can get reactions here. That's organic 2 chemistry. Okay. So if you wanted to do radical selectively, NBS is also your choice. Of course, you could always use NBS in place of bromine. Sometimes you have to use it. There is a lab, I don't think it's in the lab manual, but we sometimes do it at the very end of Organic 1, no time this summer, but where we do a bromination, which is BR2. And we pull out some lights. It's a big light bulb, and do it in the hood, and put your test tube under the light. And after a few minutes, HBr starts coming out. Because it produces HBr, right? But HBr is a gas. And, okay, I mentioned why this is important because once you get the bromine on, you can then do chemistry like we did. Here's an example of that. Here's a breast cancer drug, anastrozole. Here, I actually give this handout in Organic 2 when we talk about aromatics. That's why that's there. It's an aromatic ring up there. It's also more involved in that handout. I just cut it down to this. We start here. What are they doing? Benzoyl peroxide, NBS. Reflux 2 hours. It's carbon tetrachloride, right? They're using that as solvent. What are they doing? They're putting the bromine on the benzoic carbon. What do they do next? They then come in here with this anion, and boom, they then kick it off and do a good old SN2. That's how they get this nitrogen bonded to the carbon. You're not going to come in here and react that guy here. There's no leaving group here. You're not going to kick off an H minus, but you can kick off a Br minus leaving group. So they put a leaving group on. Why do they use carbon tet as solvent? Why not use hexane as solvent? Why not use toluene as solvent? Or xylenes. Would you use xylenes as solvent for this reaction? You use that for your Dilzolver, right? Would you use xylenes as your reaction, as a solvent? Douglas, would this be a good solvent?
It's pretty non-polar, so yes.
It's pretty what?
It's pretty non-polar, so yes.
Well, carbon 10 is non-polar, that's what they use. No, it would not. You would brominate your benzoic carbons of your solvent. Right? It's kind of melted just like that. right? You don't want your solvent to get brominated, or, you know, you want an inert solvent. Well, you can also radical brominate this, although it would be primary, well, you can make secondary. Why do you think they use this? There's no CHs. You're not going to do any radical chemistry with your solvent. Now, chloroform is like a better solvent, but if you use that, the bromine radical could strip an H out of your solvent. We don't want that. That's why they use a carbon tet. That's a common solvent for radical reactions. Carbon tetrachloride. So there's an example. Okay, tomorrow we'll look at the next page where we're going to do something we skipped back then. Remember that puzzle? Alkene puzzle that's actually on there? Anti-McCartney addition of HBr to alkenes. Okay? This is good old standard HBr addition. Or you can make cation, left or right? On the left, that's where the bromine is. Well, how do you get the bromine adding on the right?
Peroxide.
Peroxide. This is called anti-McCartney addition. Okay? Well, guess what? If you add peroxides to the HBr, you'll get this. What do the peroxides do? It makes it become a radical reaction. We'll look at this radical reaction tomorrow. See some of you in lab this afternoon, upstairs at 1 o'clock.